Hello everyone, we are Team 1 for Lab L02. I am Terrera and my group members are Jack, Kevin, and Oscar. We will be delivering a progress report for the testing and analysis of an internal combustion engine. The overall goal for Birdell Incorporated is to determine system parameters and control for an IC engine, resulting in optimal power generation. To meet the goal of the client, Generative Energy Systems, the firm will determine the engine's mechanical properties, such as frictional torque and flywheel inertia using head-off acceleration testing, characterize the full four-stroke cycle of the engine. This includes intake, compression, power, and exhaust strokes, and this will be achieved through head-on steady-state testing. Model engine output with simulated combustion with pneumatic control testing, and update a work kinetic energy model to account for the injection of air during the power stroke. Finally, we will be conducting an uncertainty analysis for all experimental terms in the work equation. On the left, our experimental setup is shown, including a force transducer to measure voltage and digital encoder to measure position. The intake and exhaust valves provide a path for fuel into and exiting the cylinder. The crankshaft is connected to the piston head and delivers rotational motion to the motor. Our experiment plan has been conducted over 2 weeks so far. The top dead center is the piston's highest point, while the bottom dead center is the piston's lowest point. During week 1, the engine head is removed, the piston remains at top dead center, and the encoder reading is at 0. At the current stage, the engine head is replaced to model effects of pressurization. The force transducer is also calibrated at every stage. Here is a table showing the measured physical dimensions of the IC engine, which will be later used for a motor work uncertainty analysis. The bore diameter, top dead center, and bottom dead center were measured using a digital caliper, and the calibration masses were measured using an electric mass scale. Now we will be presenting calibration and angular velocity results from week 1. To calibrate the force transducer, the moment arm was progressively loaded from 0 to 4 masses, then progressively unloaded one by one. Each mass weighed approximately 0.226 kilograms. A voltage was recorded at each stage. A York regression was then performed on voltage versus torque data to obtain the gain and offset values.
Here are the calibration equations for each week, showing the York fit. As shown, there is a slight hysteresis effect during the loading and unloading of the force transducer. The gain remains relatively consistent between weeks 1 and 2, but the offset value decreases for week 2 calibration. These plots show averaged angular velocity data versus angular position for steady-state angular velocities at low, medium, and high speeds, and with 4 flywheels attached to the engine. These graphs correspond to input voltages of 0.3, 0.6, and 0.9 volts from left to right. As shown, between the test start and the steady-state position, there is a rapid increase in angular velocity. For example, the medium speed test reached a steady-state angular velocity of approximately 2,500 degrees per second between points B and C. These plots show averaged angular velocity data versus angular position with only one flywheel attached to the engine. It is observed that there is an increase in angular velocity between 0.3 and 0.6 volts, as well as an increase between 0.6 and 0.9 volts. Now we will be presenting torque, moment of inertia, and work kinetic energy results from week 1. The IC engine balance equation is shown. The kinetic energy of the flywheel is integrated between points B and A. During week 1, the work done by air pressure is eliminated because air pressure effects are removed by the system during head-off testing. It is also assumed that there is no loss of work energy through the piston, and so the work due to piston movement is 0. Blue terms are determined experimentally, including the moment of inertia, while red terms are directly measured, including the angular velocity of the flywheel and the work done by the electric motor. Now we can see motor torque versus angular position data for 4 flywheels and for varying RPMs. The motor work is the area highlighted in blue above torque data, and work due to friction, shown in yellow, is above the steady-state portion of the plot. For each speed, the frictional torque, shown in red, is obtained by averaging the steady-state torques. We can observe that the starting torque magnitudes increase as voltage input increases.
This experiment is repeated for only one flywheel attached to the engine. We observe that more work is done as the voltage increases, since there is a noticeable dip at the start of the plot for 0.6 volts. Frictional torque is calculated in the same way as stated previously. The calculation of the experimental I-fly value, moment of inertia, depends on a number of components including the flywheel, the motor rotor, the coupler, and the crankshaft. In order to determine the moment of inertia for one flywheel, we subtract the experimentally observed I-fly value for one flywheel from the values for 4 flywheels, and then take the average. When compared to the theoretical I-fly value, there is a 5.92% error. This table displays the frictional torque, I-fly, motor work, and uncertainty values for 1 and 4 flywheels at varying speeds and voltages. The T friction value at 0.9 volts, the high-speed case, for both 1 and 4 flywheels are approximately scaled 1.8 times the values at 0.3 volts, the low-speed case. The motor work and uncertainty values all increase as voltage input increases. This is expected as the torque is increased for a faster angular velocity. This plot shows how the steady-state velocity affects frictional torque for the 1 and 4 flywheel cases. Torque friction can be modeled using the Newtonian model, as these values more than double between low and high speeds. To summarize results from the head-off acceleration test, increases in voltage inputs led to increases in the angular position required to reach steady state, as expected. The magnitude of frictional torque also increased when voltage inputs were increased. An uncertainty analysis also shows that theoretical I-fly and frictional torque values differ from experimental values because of the uncertainties in physical dimension calculations. These will all propagate to the uncertainty of the motor work in the final stage of the experiment and analysis. The uncertainties due to the linear York fit are also shown below. Since, as previously displayed, the York fit fitted linear curve models the calibration data relatively well, as determined by low root mean squared error, the uncertainty values due to the York fit are extremely low. Now we will present a detailed overview of week 2 experimental methods.
In an effort to assess the work of air during each stroke, the same velocity and motor torque analysis will be conducted for low, medium, and high speeds with the engine head on. The force transducer has also been recalibrated at this stage. A work kinetic energy analysis has been conducted and updated to include work due to compression and expansion. A 4-stroke representative cycle has also been characterized by averaging across multiple cycles. Uncertainty values for torque measurement, angular displacement, and work done by the motor will be determined. At this stage of data collection, we expect to calculate the theoretical work of air using adiabatic compression and adiabatic expansion modeling assumptions. The experimental work of air during each stroke will be calculated by numerically integrating torque values across a range of angles. Discrepancies in these values will be analyzed, and the effect of 1 versus 4 flywheel masses for the head-on will be discussed. Theory predicts that with more flywheel masses, the additional moment of inertia will allow for a larger retention of angular velocity between strokes and thus smoother engine operation. Now we will present results from stroke characterization. Here we see the representative cycle for velocity and torque versus angular position. On the left, we can see that angular velocity decreases during compression and increases during the power stroke. On the right, we can see that a dip in torque at the end of the compression stroke is caused by energy being exchanged between the flywheel and the air, lessening the impact on the motor. Each stroke corresponds to 180 degrees in the cycle, starting with intake, then compression, then power, then exhaust. Now we will present an overview of week 3 experimental methods. At this stage, we expect to recalibrate the force transducer again. We will be using the engine to power the motor and determining which injection angle range optimizes the power output. We will also calculate the power generated by the motor for the maximum generation case and highlight limitations of the system. A full uncertainty analysis will be conducted to calculate the total uncertainty due to terms in the work energy equation. Thank you all for listening. Please refer to the appendix for more figures, tables, equations, and references.